So this is video one and the electrical overview for the solar electric vehicle team. Here I am using MATLAB Simulinks as well as Simscape, which is an add-on in MATLAB. Click here, go down to Simulink. These are your basic blocks for Simulink. Simscape is down here. It's an add-on. You can get it for like $10 when you do the student version. In there we have power systems, electronics, electronics such as sensor sources, passive devices, we'll see switches, etc. For our battery system, this system right here is for a 24 volt motor. As explained earlier, we can use MATLAB's to evaluate how many batteries we need in our system. So we have a 24, let's do this, motor V is equal to 24 volts. We want to figure out how many cells we need, and the nominal voltage of a cell is equal to approximately 3.3 volts. Okay, so to figure out how many cells we need, we take the motor voltage, divide that by the nominal voltage of the cell, we'll call this number of cells in series is equal to the ceiling, which is just basically rounding up the number of cells we need. So if we get 7.5 cells, obviously you can't have half a cell, so this will give us that. And we have 8 cells in series. So we look back to the diagram, 1, 2, 3, 4, 5, 6, 7, 8. We can ignore this part of the circuit for now. Basically what we have here is our 8 batteries in series. We have the ANs. I call these AN. They are the Arduino analog inputs. And as explained in our meeting, the voltage on these batteries ranges, and we can look at the PDF to check that out. And we'll see here, voltage nominal 3.3 volts. When fully charged, they can go anywhere from, at the high 3.5 down to the low 2 volts. Now, one of the problems using the Arduino as our analog or controller for this battery management system or any other telemetry is that the maximum voltage into the Arduino is 5 volts. And let's go ahead and go back into MATLAB real quick. So we know we have 5 volts, so our resolution of the Arduino is equal to 5 volts, and it has, I believe, an 8-bit converter, a 10-bit converter, which is 1024 actual bits that can go into it, so 1024. So the Arduino has a resolution of 4.9 millivolts. We can reconfirm that 2 raised to the 10 is 1024. So that is the resolution, or how the Arduino breaks down voltages between 0 volts would come out as 0, 2.5 volts out of 5 times 1024. That'll give us if we see a 2.5 volts reading, it'll be displayed as 512 in the analog to digital converter. So in order to get around over voltage, so if we were to put the Arduino straight to here, it would see approximately 6.6 volts. That's over the 5-volt scale. So what we need to do is use some resistors to do a voltage division. Here we have RD1. RD1 is 100K ohms. And R2 is going to be also 100K ohms. So what we should see is the voltage at this point being split in half between RD1 and R2. That voltage then will send to the Arduino, to the analog to digital converter, and so on for the rest of the voltage dividers. What we're going to do though is we're going to increment each of RD, the resistor divider network, by 1K each time, so that the voltage appeared here should be close to 3.3 volts, or the nominal voltage of a battery. So we could do a quick voltage division. We'll show here 200K, and we have here again 1K, 100K. So we'll go back to MATLAB just to show what we should see. We have the input is 6.6 volts, and then we're going to times that by a voltage divider, and so we have the bottom resistor is 1K, 100K, 100E3, and the total resistance of that network, which is 200K plus 100K, is indeed 300 E3, 300K. Oops, that is not the right thing. Should be 9.9 volts. 9.9. So we're looking at this one right here, 2 and 1, and that will give us approximately 3.3 volts. So what we're going to be looking at is that at each point where the Arduino is doing its analog to digital conversion, the voltage should only range between 0 volts and 3.3 volts. So we're not using the full resolution of the Arduino, but we're also making sure that should these voltages rise higher, that is also capped at 5 volts here. And let's just do a quick simulation. So using Simscape, we need to convert these Simscape blocks into MATLAB. So what we have here is a little block they use that does that conversion. So this does the power to simulate converter, basically a physical system, and outputs it as a Simulink signal. We need a Simulink signal so that when we run this model, compiling, and it's done, we can open this scope, and the scope will then produce outputs. If we don't have that, basically we won't be able to use it for a scope. So here we're showing this is just for display purposes, battery voltages, all the battery voltages raising from 0 volts up to the nominal and then leveling off about 4.2. The time scale here is just 1,000 seconds. And on the right, we have a legend that shows the battery's voltages. So a couple additional things that are good about using Simscape is that we can integrate a electrical system and a mechanical system. So what you see here on the right is an DC electric motor. On the inputs is the positive and negative DC voltage applied to this motor. And then on the right, what you'll see is the mechanical equivalent, or the mechanical torque that's put out by the motor. And then here we have a rotational inertia, mechanical ground just kind of showing to complete that circuit of that system. And then we can look at the pack voltage here, which should be the output of the pack voltage. And we can bring that onto the screen. And here you're seeing the pack voltage rise to about 33 volts. So not to get too hung up on Simulink and Simscape, but here I have a constant current coming in, charging these batteries. That would be something that would eventually come out of our maximum power point tracker from the solar cells to charge the battery packs. The last thing to mention here is that in order to use Simscape's physical models and convert it into Simulink, we need to also have a solver configuration here, and it can be applied anywhere in this schematic. For the next video, we'll talk about how we are going to implement this part of the design on Eagle, and something that I have been advising to the other students is using Eagle for the purpose of board design. The reason we want to use Eagle and the board design is that so that we can get a Fusion Sync, which would be a physical model of this board in Autodesk Fusion 360. So here we have the rough draft of this BMS and its physical dimensions, size, pin headers, etc. How it will connect to an Arduino Mega later on, we'll show that. And we also have a full car assembly, and this is where we'll be able to track all the different projects that are going on in the car. So here I have a motor that was a NEMA motor that had a STL file. We loaded it in. Here is just a rough draft example of a battery pack and the BMS. So as we edit and modify this BMS, it will be pushed to this assembly design so that we can track the progress of this project as well as other projects that are involved, such as the battery pack, the frame, wheel design, brakes, etc.